Welcome to the debate. Today we're focusing our lens on a component that really sits quietly at the very edge of the electronic frontier. It's the device that stands between the raw, messy physical world and, well, the ordered logic of our digital systems. We are talking about the Instrumentation Amplifier.
It's a fascinating piece of silicone, isn't it? For most engineers, it's just a kind of black box, a triangle they drop into a schematic when they need to read a sensor. But when you look at the source material, specifically this power of precision overview, there is a deep philosophical divide here.
There is a divide that really centers on the very soul of the component. When we look at this architecture of accuracy, does the value of the instrumentation amplifier lie in its internal pursuit of mathematical perfection? Approximating the ideal infinite input impedance and precise gain? Or is it something else?
Well, I'd argue the ideal is a distraction. The true value, the whole reason this component even exists, is its external robustness. It's about survival. It's about the ability to reject the chaotic common mode noise of the real world. I mean, you can have all the internal precision you want, but if you can't survive on the factory floor, you have nothing.
I fundamentally disagree. The noise is a variable. Yes, I'll grant you that. But the IA's defining virtue is fidelity. As we see right in the data table, the IA is an engineering marvel because it bridges that gap between the ideal requirements and a practical range. It captures a signal without altering the source. It's a transparent window into physics.
A window is pretty useless if it's covered in mud. My stance is that the defining virtue is rejection. We're looking at the industrial sensor and the noise sections. The heart of the matter is the common mode rejection ratio, or CMRR. It's not a window, it's a shield.
Well, let's get into the specifics then. I want to anchor my position statement right in that data table from our source material. When we talk about measuring the physical world, temperature, pressure, strain, we're usually talking about very delicate phenomena. The source explicitly mentions weak signals in the range of millivolts or even microvolts.
Tiny signals, barely a whisper of electricity.
Extremely tiny. Now, look at the amplifier requirements listed there. The first and most critical spec listed is input impedance. The ideal requirement is listed as infinity. Now, obviously we can't achieve true infinity in the physical universe, but the practical range achieved by the IA is listed as extremely high. This isn't just a number on a datasheet. This is a philosophy of non-interference.
Non-interference is a nice term, but explain what you mean practically.
I mean, not loading the source. Imagine your sensor is, say, a small battery with very high internal resistance. If your amplifier has a low input impedance, it's essentially asking that tiny battery to deliver current. And when you draw current through that internal resistance, the voltage sags. You're no longer measuring the true open circuit voltage, you're measuring the voltage under load.
So you're changing the data just by looking at it.
Precisely. You essentially destroy the integrity of the measurement just by connecting the wires. The instrumentation amplifier, with that extremely high input impedance, we're talking gigaohms sometimes, it asks for almost zero current. It observes the voltage without touching the energy. It allows the sensor to speak without draining its lungs. That is the precision in the title.
That is a beautiful classroom theory. It really is. But let me give you a different perspective drawn from the left side of our source material. You're talking about preserving the signal at the source. I'm talking about what happens to that signal before it ever even reaches the amplifier.
So you're referring to the cabling?
I am. The diagram shows an industrial sensor connected to long cables. And what are those cables doing? They're all coiled up. And surrounding those coils are these jagged orange lines representing noise and interference. The source explicitly links this to, and I'm quoting, lightning bolts of electrical noise.
Sure, noise is a factor.
It's not just a factor, it's the dominant reality. In the real world, signals travel through hostile territory. The material says the IEA's job is to reject common mode noise. It uses a high common mode rejection ratio, CMRR, to eliminate interference from long wires.
But if you don't have the impedance, you don't have a signal to begin with.
And if you don't have rejection, you have the wrong signal. If you have that perfect input impedance you love so much, but you have a low CMRR, you are simply going to measure the hum of a 60 Hz power line with exquisite precision. The IA is a filter against chaos. The differential nature, that's the key. The ability to look at two wires, see that they both have the same voltage spike, and just delete that spike mathematically. That is survival.
That's an interesting point that I would frame it differently. You're acting as if this noise rejection can exist independently of the input structure. But let's look at the core debate here. Let's talk about that impedance versus the environment in a specific context.
Let's do it.
I want to go back to the weak signals, the millivolts or microvolts. The source material highlights this for a reason. In a data acquisition system, which is shown as one of the real-world applications, the IA acts as the intermediate stage between a transducer bridge and a display device.
The Wheatstone Bridge. A classic circuit.
It is classic because it works on balance. You have 4 resistors in a diamond shape. The signal is the tiny voltage difference between the 2 middle points. And this is where your argument for survival over precision kind of falls apart. A bridge circuit has a very specific output resistance.
Sure.
If the IA doesn't have that extremely high input impedance, it acts as another resistor in parallel with the bridge legs. It unbalances the diamond. It creates a nonlinear error. You aren't just adding noise, you are warping the entire curve of the measurement. So if you're weighing a truck on a scale or measuring pressure in a pipe, that impedance mismatch means the scale reads 10% light. No amount of noise rejection fixes a lie that you told yourself at the input terminal.
I see the elegance in that. I do. You want to preserve the integrity of the bridge math. But I'm looking at the real-world applications listed down at the bottom, specifically the temperature control systems. The graphic shows a vat, maybe in a plastic or dairy plant, with heaters and relays all over it.
It does.
Do you know what the electromagnetic environment of a dairy plant looks like?
I can imagine it's not quiet.
It's an electrical war zone. You have massive induction motors driving pumps. You have variable frequency drives chopping up waveforms. You have heater relays snapping open and closed. And every time a relay snaps, it sends a magnetic pulse through the air.
Which then induces current in the cables.
Precisely. The long cables in that diagram act as the secondary winding of a transformer. The motor is the primary. That noise appears on both wires going to the amplifier. That is common mode. Now imagine your scenario. You've built a system with perfect input impedance. You haven't loaded the bridge, but you have poor CMRR.
The signal is clean leaving the sensor.
The signal was clean leaving the sensor, but by the time it travels 50 feet to the control panel, it is riding on top of a 5-volt spike from the pump turning on. If the IA can't subtract that spike, the temperature reading jumps. The control system thinks the milk is boiling and shuts down the pasteurizer. Or worse, it thinks the plastic is too cold and turns on the heater, burning the entire batch. In that moment, the high impedance didn't save the batch. The subtraction saved the batch.
I'm not denying the utility of rejection, but you are describing a failure of the environment, not a virtue of the amplifier. You fix that with shielded cable and proper grounding.
In a perfect world, yes. But in a retrofit in a 40-year-old factory, the IA is the last line of defense. It's the goalie. It has to make the save when the shielding fails.
Fair enough. But let's look at another aspect of the data table that really drives my argument for internal precision. Gain control, using the R sub G resistor.
Ah, the single resistor.
It's not just a resistor, it's a definition of scale. The diagram highlights that a single external variable resistor, RG, allows the gain to be adjusted from 1 to 1,000. And crucially, the requirement is stable and accurate.
It is convenient, I'll grant you.
It's more than convenient. Look at the light intensity meters application. We're measuring lux. Light is a physical quantity that spans huge dynamic ranges. You need to be able to scale your measurements strictly. If I set a gain of 1,000, I need to know it is exactly 1,000, not 950, not 1050.
And why is that specific number so critical to you?
Because of linearity. If I am calibrating a medical device or a scientific instrument, I need a linear relationship between the photon hitting the sensor and the number on the screen. The stable and accurate requirement ensures that the internal components of the IA don't drift with temperature.
If the silicon heats up and the gain changes, the measurement is a lie. That power of precision allows us to trust the number.
I'm not convinced by that line of reasoning because it completely ignores the danger of what you are doing. You say gain of 1,000, I hear amplification of hazard.
How so?
Gain is a multiplier. It's blind. It multiplies everything that gets through the gate. If your common mode rejection isn't perfect, and nothing is perfect, some of that interference from long wires gets through. And if you crank that gain to 1,000 times because you're chasing a weak signal, you are also cranking up the noise 1,000 times.
That's why the precision is necessary, to keep the noise floor stable.
No, the power of precision is actually the power of exclusion. What the amplifier refuses to see is more important than how much it multiplies what it does see. In that temperature control system, if a relay kicks on and spikes the line and you amplify that spike by 1,000, you trigger a false alarm. The RAG is a dangerous tool if the input stage hasn't done its job of rejection first.
But consider the photocell sensor mentioned in the source. It says it is used to replace thermistors. Photocells are nonlinear, they're finicky. The IA provides a stable gain environment that allows us to linearize that data. If we focus entirely on noise rejection, we treat the signal as some combatant to be rescued. But in the case of the light meter, the signal is information to be translated. The IA is about preserving the fidelity of that information.
It is minimalist, I'll grant you that. But let's look at the transducer bridge diagram again. You see the 4 resistors.
Yes.
And it feeds into the IA, and then into the data acquisition systems. Now look at the industrial sensor graphic again. It specifically labels weak signals, millivolt or microvolt.
We established they are small.
But just think about the scale. A microvolt is 1/1,000,000th of a volt. In a factory environment, the electromagnetic radiation from the overhead LED lights alone is inducing more than a microvolt of noise on any wire longer than a few inches.
Which is why we use twisted pairs.
Sure, but the IA is the final arbiter. The way I see it, the IA is a protective barrier. It allows the sensor to exist in a hostile world. The photocell sensor is a sensitive analog device. Without the IA's rejection capabilities, you couldn't put a photocell anywhere near a running machine. You couldn't use it in a temperature control system for a plastic plant because the heaters would blind it. The IA allows these delicate sensors to function in places they really have no business being.
I think we're touching on something important here regarding that transducer bridge. The diagram shows it connected to the IA, and I view this as a translation task. The bridge speaks the language of resistance changes, strain, temperature, light. The display speaks the language of voltage. The IA is the translator.
And I view it as a bodyguard.
A bodyguard.
Absolutely. The bridge is a civilian walking through a war zone. The IA ensures it gets to the safe house, the data acquisition system, alive. I mean, if you look at the noise and interference visual, those jagged lines are aggressive. They are attacking the long cables. The IA doesn't just translate, it extracts the survivor.
But let's look at the data table one more time. Under amplifier requirements, it lists gain, ideal requirement, stable and accurate. It doesn't say gain high, it says stable.
Fair.
This implies that the quality of the amplification is paramount. If I am running a temperature control system in a dairy plant, as the graphic suggests, precision is a safety issue. If the milk needs to be pasteurized at exactly 72 degrees Celsius and my amplifier drifts because it isn't stable and I read 72 when it's actually 68, I have a public health hazard.
Or if the noise from the heater relay makes the reading jump to 80, the system shuts down prematurely.
But the drift is internal. That's my point. The stable requirement refers to the internal components of the IA. If the silicon itself varies with temperature or time, the noise rejection doesn't matter. You are generating your own error. The precision in the power of precision refers to the device's ability to be a constant in a world of variables.
And yet the real-world applications are all loops. The temperature system drives relays, the light meter drives a display, the transducer drives data acquisition. These are feedback loops. And in a loop, stability is important, but your signal-to-noise ratio is critical. If you have a stable gain, but a low signal-to-noise ratio because of poor CMRR, your control loop oscillates. Your heater turns on and off rapidly. You burn out the relay. The rejection of common mode noise is what stabilizes the system, not just the amplifier.
I think we are looking at the same diagram and seeing two completely different stories. You see the jagged lines of interference as the protagonist, or, I guess, the antagonist.
I do.
And I see the clean sine wave inside the green triangle of the IA as the protagonist. Look at the central graphic. The instrumentation amplifier IA is a large, clean triangle. Inside, there is a perfect sine wave.
It is very clean.
Pure wave. The power of precision title implies that this purity is the goal. The ability to take a millivolt signal and turn it into that perfect sine wave on the display. That requires the high input impedance to catch the wave and the precise gain to shape it.
And I look at that same central graphic, and I see the two arrows coming into the funnels. One is the signal, one is the inverted reference, the differential pair. And I see the rejects common mode noise label pointing right at the input. That is the gatekeeper. That is the bouncer at the club. That perfect sine wave inside, it only exists because the bouncer did his job. If the bouncer lets the riffraff in, the common mode noise, that sine wave becomes a scribble.
But if the club has no atmosphere, if the gain is wrong or the impedance loads the source, it doesn't matter who gets in. The party is ruined anyway.
That's a fair analogy.
There is one more spec we have to discuss. We have spent a lot of time at the input, but I want to drag your attention to the other side of the data table. Output impedance. Ideal? 0. Practical? Extremely low.
That's just standard op-amp behavior. Why is that a debate point?
Because the IA isn't an island. It has to drive a load. Look at the data acquisition system diagram. The IA feeds into an ADC or a display. In a real facility, that display might be 50 feet away in a control room.
More long cables.
Exactly. If the IA had high output impedance, the voltage would drop across that long wire. You'd lose the signal you just fought so hard to capture. But extremely low output impedance means the IA has authority. It can push current, it can drive the capacitive load of a long cable without oscillating. It's another form of precision, the precision of will, if you like, the ability to enforce the measurement on the rest of the system.
That's a compelling argument, but have you considered that the output stage is usually less vulnerable than the input? I mean, the input is dealing with microvolts. The output is dealing with volts.
True, the signal is larger.
The signal-to-noise ratio at the output is already 1,000 times better thanks to the gain. So the survival happened at the input stage. The output stage is just the victory lap. The real work, the heavy lifting of eliminating interference, happened at the front door. If the input stage fails to reject the common mode noise, the output stage is just driving garbage down the line with great authority.
I suppose that depends on how much you trust your environment.
In a plastic plant, I trust nothing.
Fair enough. But I maintain that the low output impedance is what allows the IA to integrate into the architecture of accuracy. It ensures that the IA is not just a sensor interface, but a reliable source for the digital world. It is the handover point.
As we wrap this up, I keep thinking about the industrial sensor sitting on that metal block in the diagram. It looks solitary. It looks vulnerable. And the IA is its only link to the world of meaning.
It is the bridge.
My closing thought is this. The instrumentation amplifier is the standard not because it's perfect, but because it's tough. It acknowledges the flaws of the physical world. It survives the long cables. It survives the lightning bolts of interference. It uses CMRR to carve a signal out of the noise. It represents the triumph of signal over chaos.
And I will maintain that the instrumentation amplifier is the standard because it respects the laws of measurement. It abides by the rule, do not disturb the observed system, which gives us the high input impedance. And it abides by the rule, report the findings accurately, which gives us the precise gain. It represents the power of precision in its purest form. It's the closest we get to a mathematical ideal in a dirty world.
Perhaps it's that tension that makes it so ubiquitous.
I think you're right. It sits exactly at that intersection. It deals with delicate physics, those weak signals, and it has to deal with harsh reality, that industrial noise.
It needs the high impedance for the physics and the high rejection for the reality.
Exactly. It's a component that has to look in two directions at once, inward toward the ideal and outward toward the chaos.
And without both, that data acquisition screen would just be blank. Or worse, it would be lying to us.
A sobering thought for anyone relying on a temperature controller today. That brings us to the end of this debate. We hope this has illuminated the complex architecture behind this essential component.
Whether you value the math or the survival, there's no denying the utility.
Indeed. Thank you for listening.
Until next time.